So I'm going to share my screen now. We tried this out, so hopefully it. Okay, well, thank you, Adriana. That's a lot of pressure you're putting on me there that you haven't had anything like this before. So I hope it's everything you expect or we're anticipating it to be. I'm going to talk with you today about hydroelectric power. My name's John Stoessel. I'm an engineer with Southern California Edison. I actually work in the audits department at Edison right now, but for 16 years of my 23 years at Edison, I was in the dam safety group, where we were responsible for making sure that our dams were being operated safely, both for our business and for the public at large, our customers. Also, I'd like to say that if you do have any questions and you want to come off mute to ask those, I don't have a problem with that. You know, at least at this point, if it becomes too much of a burden on the presentation, I'll make that known. But if you want to put something in the chat, that's fine. If you want to come off mute and interrupt me to ask a question, I'm okay with that as well. So I always like to start out with a little bit of humor. And since I'm an engineer, I never hesitate at an opportunity to kind of poke fun at engineers, myself and my profession. And there may be some of you there that are considering pursuing a career in engineering. So I thought I'd let you know what people think engineers are doing. So here's some photographs of, if we start from the upper left corner, what my friends think I do. They think engineers are always studying, engineering majors, engineering students in college. What my mom thinks I do, same thing. My mom thinks I'm just studying all the time. What everyone else thinks I do, studying all the time. What my professor thinks I do is studying all the time. However, what I think I do is what I enjoy doing is tinkering around on exotic automobiles. But then reality sets in, and the last is what I actually do, and that's studying all the time. So I don't want to scare people away from being engineers and pursuing that as a career, but it does take there's a lot of emphasis on education, and there's a lot of studying that goes along with that. So with that, we'll get right into talking about hydro. So first of all, the power of water. I don't know how many of you have actually seen something like this or experienced it, or you've seen a large waterfall where you can really get a feel visually, sound, the feel of the power of water, how much power you can get out of water when you harness it. And this is just a picture of a dam releasing water, a large amount of water, and you can just see how much power there is in that water. Just imagine anything in the way of that is going to get moved very quickly. It's going to be hard to resist the power that's producing. And one of the things that we do as engineers is we look at things like this, these physical things in nature and in the world that are going on around us. And we try to think, how can we harness this? How can we use this power in constructive, beneficial ways to help society and to improve the lives and quality of life of people? And maybe one way that you can kind of understand this, if you haven't seen this before, is just think about having a garden hose with a nozzle on it. And the water's coming out of the end of the garden hose, and you put your hand right in front of the nozzle, and you'll feel the pressure that the water's pushing against you. And that's kind of what we have here, is that's the work that water can do. It wants to push your hand away. That's work. Now you just expand that to a much larger degree when you have something like this, and the amount of energy that you can harness out of that. So let's talk about the physics of hydropower. How does hydropower work? And it's actually quite simple But as anything else, the devil's in the details. But we're gonna really boil it down to the three simple concepts that you have to understand of how hydropower works. The first one is you have a water source at a higher elevation that has the potential to do work. We call that potential energy. That water at a higher level can do work. But while it's there, it's kind of like a battery. It has stored energy waiting to be released in some way. So how does that energy get released? Well, we provide a means of moving that water from the higher elevation to a lower elevation. And what that does is it allows us to take that potential energy in that water at the higher elevation and convert it into kinetic energy, which is moving energy. So the water initially is stationary up there, wherever it is, higher than us, but we connect it with, say, a pipe that allows us to bring it down to our elevation, which is lower. And when we release to let that water run through that pipe, when it comes down to us, that water is now moving. It has velocity and it has kinetic energy. And then what we can do is we can transfer that kinetic energy to a wheel that we can connect to some device that we can perform some type of work. In hydropower, it's going to be turning a generator to make electricity. But you know, throughout history, we've used hydropower even long before we actually had discovered energy and figured out how to harness it and use it the way we do today. So here's the history of hydropower. It was first harnessed back in Roman times by the Romans 2,100 years ago. Now, they weren't making electricity with it because they didn't know electricity other than maybe when they saw lightning storms or static electricity that they might, experience if they got in dry climates when you can generate it depending on the surfaces you're walking on, and then they'd get close to something that would discharge and you feel a little spark. So they knew about electricity, probably didn't understand it, what it was, and they certainly didn't know how to produce it, how to manufacture it. But they were using water, harnessing the energy of water to do work. They might have used it for grinding grain or for doing some other type of activity. However, the first hydro plants that were built in the United States, first one was built in 1882. So that's 140 years ago, 240 years ago. 200? Got to get my math here. 340 years ago that they built the first hydro plant. So now we look at where we are today, and hydropower provides about 7% of the electricity that we use in the United States. So it's a major contributor to our energy system that we have in the United States. However, if we look at the entire world, it provides about 16% of the world's electricity use. So it's about 2.5 times what we use in the United States if we look at it worldwide. That 16% is made up of about 150 countries. So not every country has the ability to use hydropower because they don't have the water sources for it, or they don't have an economy that allows them to develop hydroelectric power. That 16% represents more energy than is produced by either nuclear power or oil generating plants. And out of those 150 countries, 4 countries use 50% of the world's hydropower. And those 4 countries are China, Brazil, Canada, and the USA. And that's in order of use. So China is by far the largest user of hydroelectric power in the world. They have lots of water. They have lots of rain that produces conditions where they get lots of runoff and lots of water stored so they can use that to generate electricity. But then there's countries like Norway where almost all of their electricity is produced by hydropower. So they don't use nuclear, they don't use solar, they use solar, but the majority of their power is produced by hydroelectric generation. I think Norway, it's clearly over 90%. So how do we generate electricity with water? Well, this is a fairly simplified drawing here of how that works. We have a dam, of course, that holds back water. It impounds water in what we call a reservoir. And that reservoir can be very large or much smaller, but it holds a body of water stored. And we then take and put a generator and turbine at a lower elevation. Remember what I said about going from higher elevation to lower elevation. So we've got this water stored. Again, think of it as just like a big battery, but it's water instead of electricity that's stored in there. And then what we do is we direct that water to a turbine, which is a wheel that has paddles on it. And when that water comes, when we release that water and let it flow, because it's going to gravity, it's going to start flowing through the penstock in the picture, and it's going to turn that wheel. And that wheel is going to be connected with a shaft to a generator. And a generator is just the reverse of an electric motor. Instead of electricity turning an electric motor that allows it to do some work, we have a electric motor turning, and it makes electricity. And that's the way this works, is the turbine is being turned by the water, and it turns the generator. The generator generates electricity, and then it goes out of the powerhouse to power lines that take it to businesses and homes and everywhere else that it's needed. So it's a simple view of electric power. And as I said earlier, we can get it down to the three basic concepts of having water stored at a higher elevation, and the top of the surface of this reservoir in this picture is higher than the turbine. Then we have to have a way of getting the water to the turbine, which is what we call a penstock, just a pipe or an opening. And then we turn, and when that water comes through, it's moving, and that kinetic energy is now transferred to that wheel that turns and generates power. But I also said the devil's in the details. So there's a lot of work that goes into making this actually happen, to where you can then turn your lights on in your house and they come on because there's a hydroelectric plant somewhere far away that's generating that electricity. But that's really not what we're here. We're not here to talk about those details today. We're just here to talk about hydroelectric power in general. So we'll move on. So there's three types of hydroelectric plants that you can have. And the first is what we call an impoundment hydropower, or impoundment hydropower method of generating electricity. And that's what I was just showing in the previous slide. You have a dam that impounds a reservoir, a body of water at a higher elevation, or higher reservoir, as it says here. And then you have a way of moving that water to a lower elevation, to a turbine that you can spin with a generator, and that produces electricity. And hopefully some of you, or maybe all of you, have seen a dam before. Maybe you've driven over it in a car, or driven by one when you're in a car, or gone hiking someplace where they have one out in the mountains. And so you have an idea of what a dam is, but it's basically just it's a structure that's holding back a body of water. So that's one way that we can do it. A second way is what we call a run-of-the-river hydropower. Now that's a little bit different in that instead of having a dam that backs the water up into a reservoir, you have a river that runs. And we know that rivers will run from higher elevation to lower elevation. Water doesn't go uphill, it only goes downhill. And water is always trying to find a lower elevation. And eventually all water wants to try to get to the ocean, because that's sea level, that's the lowest level, that's where all water wants to get. And that's why here in Los Angeles, when it rains, we get a lot of water coming out of the mountains, and it all wants to run down to the ocean. Now we can do, like the previous slide showed, we can build a dam up there and store that water but we can also use the river where we can, at some point higher up on the river, we can divert some of that water. We can have a way of splitting that water. So some of it still continues down the river, but some of it follows a different path down. It could be a pipe, it could be a channel or something that directs the water from that point down to a generating station. And this way, as long as the river has water flowing to it and we can take some of that water, we can run the turbine and the generator and make electricity. Now, the disadvantage to this process is that rivers typically will flow more and less throughout the year. They'll flow heavy when you get rain and snow melt feeding the rivers from higher up elevations. But then as the weather tends to move away from rain and the snow's all melted, the river flow will start to reduce. So you can't maintain a constant generation of electricity because you don't have consistent volume of water throughout the year. There's advantages to this. It's less environmentally intrusive than building a dam, but it also doesn't have the reliable generation throughout the entire year because of the cycle that the water will run through this river. So that's a second way. A third way, and this is a really interesting process, it's called pump storage. Now, this takes advantage of not a physics issue, because in physics, we know that we can never get back out what we put in. That's a fundamental law of nature, is that we have to put more energy in than we get out. The best we could ever do if we were fortunate is we could break even, but we can't even do that because there's certain losses that we have, like friction and heat that's generated, that take away energy of some of the energy we put in, so we can't get it all back. But the way this works, it works on economics. So what you do is you have a system set up where instead of just having a turbine generator, you can run the turbine backwards and use it as a pump. So you can run like you normally would from a reservoir with a dam. You can generate electricity, and it goes through the power plant, turns the turbine, and the generator generates electricity and releases the water into a lower reservoir. But then what you do, you run it this way when the cost of electricity is high, because the cost of electricity varies through the day. When the demand is high from people needing electricity, the price of electricity goes up. When the demand is low, the price goes down. So what you do is you run it in this direction when the price is high. And then since you have to buy electricity to pump it back, you buy it when the electricity is lower priced. And the way this works then is you're constantly recycling this water back and forth, back and forth, back and forth, but you're making it economically feasible because you can make up the difference between the high cost that you sell it at and the lower cost that you buy it at. And the difference is profit that you make. And it's renewable because you're using the same water over and over and over. So it's clean and it's renewable. But it's not the physics of it, it's the economics of it that make it work. So you might ask the question, what makes hydropower renewable? Why is it considered renewable? Well, there's a little thing called the hydrologic cycle, or the water cycle, as it's simply put. And it's a cycle because it just works in a circle. It continues to repeat itself over and over and over. And how does it work? The oceans, lakes evaporate, the water evaporates. And what causes the water to evaporate? The sun. The energy from the sun causes the water to evaporate. Now, does the water just evaporate out into space and disappear? No, because if that was the case, we would have been gone long ago, because you can't make water. So whatever water was here would eventually disappear and be completely gone, and life would not be able to continue existing. No, what happens is it evaporates, but eventually it starts to condensate in the clouds, in the form of clouds. And what happens is when the clouds get sufficiently saturated, you get rain. Or if it's at a high enough elevation, you get snow. So now you've got the rain or the snow, that's what we call precipitation, and that's now feeding into the rivers, into the snow that melts and goes into the rivers, which collect it. And what do? They send it right back to the ocean. So it's a cycle. We don't create water, we don't destroy water, we just keep using it over and over. So that's what makes it renewable, because it isn't a resource like, let's say, oil, where there's a finite amount of it, and when you burn it, you don't get it back. Or even nuclear, when you run a nuclear power plant with uranium, the uranium doesn't last forever. It depletes, and eventually it doesn't work anymore, and it doesn't go back to the same thing it was before. So you can't use it again. So that's why we call hydropower a renewable resource. Now, I want to talk a little bit about the types of dams that there are, since they're pretty important in most of the hydro generation methods. You know, we had the run of the river, which doesn't require a dam, but the majority of the power that's produced, electric power that's produced by hydro, uses very large dams. So what are all the different types of dams? Well, there's a concrete gravity dam. And how does this dam work? Well, in its name kind of describes how it works, concrete gravity. It's a massive amount of concrete that, just due to the weight of that concrete, it's able to hold back all that water. So these are very thick, large structures of solid concrete that, just based on their sheer weight, are able to keep the water back. And an interesting thing that might be a little hard to grasp at first, but when you have a dam like this, you have a very large reservoir behind it. Whether that reservoir extended 1 inch behind the dam or 100 miles behind the dam, the force on the dam is exactly the same, because it's only based on the height of the water, not on the volume of the water. There's a concrete arch dam. Now, in some situations, you can't get all of that concrete to the location that you're building a dam. You can't put enough concrete there because of its location, of getting the material to that location, or just maybe the way the geography of that area. So you have to figure out a way to build with less concrete. So instead of relying on just the weight holding the water back, you build the dam in an arch shape. And what that does is it takes the weight, the amount of force that the water's pushing against the dam, and instead of the weight holding it back, it's the strength of that concrete that forces the resistance into the ends of the dam, into those what we call abutments, or in this case, you can see they're these hillsides on either side of the end of the dam. That's what's resisting the water pushing against the dam, is all at the end pushing back against it. And the dam wants to bend, and the arch action is, and concrete is designed to be able to resist that bending and push all the load into the arches at the end to hold it back. And with this, you can use a lot less concrete, but building something like this is much more difficult construction. So you don't use as much material, but the construction is more complex. Now there's some situations, and this happens to be one of Southern California Edison's dams. There's some situations where you can't build a single arch dam to cover an area this long. This dam from end to end is exactly 1 mile long. There's 58 arches that make up this dam. So what you do is, instead of building one big arch dam, which would not be possible, you build a bunch of little arch dams. And the reason they did this is this dam was built back in around 1920, so it's over 100 years old. Getting concrete back to this area back then, and even now, was very difficult. And the amount of concrete you would need to build, say, a gravity dam here would be impossible to have acquired that much concrete and constructed it back there that way. So this was a unique design that had been developed by an engineer named Eastwood, where he designed what he called the multi-arch dam. And as you see, it's multiple arches working their way around. So there are a bunch of little small dams connected to each other, little arch dams connected to each other. Now, it turns out that today, this dam, while it may work in some areas, it's not a design that you would use in an area that had earthquakes, large earthquakes, and issues with large earthquakes, because there's some structural weaknesses to this type of design. But these weren't known back 100 years ago. And so this dam was built. And many of these types of dams were built, some in areas where they've had to be modified because of their seismic sensitivity, and other areas where it really doesn't matter because their seismic activity is not that high. Now, there's also what we call earth fill embankment dams. And these are dams that are built out of essentially dirt, but not just any dirt that's dumped in and just piled up like you see in this picture, but very specifically designed with different types of dirt, because again, you're relying on the weight of all of this dirt to hold back the water. But you also have to worry because, you know, dirt isn't like concrete. It's much easier for water to move through dirt than it is to move through concrete. So you have to build it with different types of dirt in the interior as you move out to the outsides of the dam. And the interior, you use materials, dirt that's very, what we call impervious. It's very hard for water to move through it. And then as you move further away from that, you start to use more materials that are less impervious, because you're just trying to get the weight, the mass of dirt on there that can hold back the water. These dams are popular because many times you can build, wherever you're building them, you can use the local materials to use as the earth fill. So you don't have to bring in materials. You can get your materials from the location that you're doing the building. So it really cuts down on the costs of construction. We also have what we call a rock fill embankment dam. And this is much like the earth fill, except as the name implies, instead of using earth or dirt, you're using rock. So you just pile up a lot of rock. And again, this type of dam would be attractive to use in areas where you had a large supply of rock that you could use. In many mountains have a lot of rock, like granite, and you can mine that rock in various ways to create the material that you need to build a dam like this. Now, what you have to do on a rock-filled dam is you usually have to put some type of a face on the front of the dam that's waterproof. So they'll use concrete, a relatively thin slab of concrete over the front of the dam. So that's between the water and all the rock. Or in some cases, they use wood. And actually, Southern California Edison has 4 dams that are rock-filled wood-face dams, where they have wood planking over the face of the dam and then rock piled up behind it. And the rock again provides the weight, the mass, to resist the force of the water pushing against it. And the wood, when the reservoir fills up and the wood swells because it gets wet, it seals itself tight so the water can't move through it. Now let's talk a little bit about Southern California Edison's hydroelectric systems. We have 4 different areas that we have hydroelectric power generated in. But by far our biggest is what we call our Big Creek Hydroelectric Project. This project is located in the Sierra Nevada mountains, right near Fresno, California. I don't know how many of you are familiar with Fresno, if you've ever been up there, but if you're in Fresno and you look to the east, you're going to see the Sierra Nevada mountains. And you can see in the small inset screen, you can see in the yellow area is what's highlighted in this bigger, and then you can see Fresno right there. And we call this, or actually it was given the name, the hardest working water in the world. Now, this whole project was envisioned by an engineer named Eastwood, as I mentioned earlier. In the late 1800s, he went on horseback up into the mountains, the Sierra Nevada mountains, and he was able to visualize this whole system while he was up there doing his surveying on a horse in the mountains. Now, if you fly over this in a helicopter today, it all makes sense because you can see it from high up in the air and you can look down and you can see the whole thing and you can see how all this water that's coming down in the wintertime from melted snow has to flow down through this area, and you could build a system of dams and power plants to generate all this electricity. But we need to remember in the 1800s, they didn't have helicopters and people couldn't fly then as they can't now. So he had to do all of this on horseback, and he was able to see all of this. He was a visionary in that way, that he was able to see the potential to build this. Now, what drove this to getting done? Because there had to be a reason to build this. It's just not, oh, I see it can be done, we're going to build it. Well, it relates to the history of Los Angeles. There was a fellow named Huntington, and actually his name still is still kept alive by the Huntington Library in Pasadena, and the area that he has with all of the flowers and trees that he has as well, that people can go visit. But at that time, he was running the cable cars in California, in Southern California, and he needed electricity to run those cars. And so he worked with Eastwood to fund the building of the Big Creek Hydroelectric Project so he could take that electricity that was being generated and bring it to California, to Southern California, Los Angeles, and use it to power his cars, his street cars. Shortly after this construction started, Southern California Edison bought the power company that he started. And so that's how we became the owners of this. But it's hard to see on the screen, but you can see there's a lot of lakes identified, and you can see with these little yellow triangles, these are powerhouses that are on this water coming down through to eventually run out to the ocean. It goes through Fresno and out to the ocean. Now, why do we call this the hardest working water in the world? Well, here's the reason. 27 dams built on that water system. 27 dams, that's a lot. And remember, almost all of those dams were built between 1905 to 1920. Not today, 100 years ago. Lots of manual labor. Didn't have a lot of the machines that we have today to build things with. A lot of it was done by just brute force, people working. Miles of tunnels to move that water from one lake to the next, to the next, to the next. As it moves from the higher elevations, trying to get down to the ocean, we're going to capture it at various times to generate power off it. So we're generating power at a higher level, and then at a lower level, we're taking that same exact water and we're generating power with it again. And then at a lower level than that, taking that and generating power with it. That's why it's called the hardest working water in the world, because we keep working it over and over and over until it finally gets down to the bottom, and then we let it go and the farmers use it, and then eventually whatever's left gets out to the ocean. But there's more. 9 powerhouses. Those are the places where we generate the electricity. There's 9 of them on this system of 27 dams. So that's why you have to have all these tunnels, because you don't have a powerhouse with every dam. So you have to be able to move the water from dam to dam to these powerhouses so you can generate power with them. And within those 9 powerhouses, we have 24 generating units, 24 of those turbines that are being used to generate electricity. And with all of that, we get a capacity of more than 1,000 megawatts. That's a lot of energy. That's enough, I think, to service about 500,000 to 1 million homes in California. So it's pretty amazing. That's why we call it the hardest working water in the world. Now, that may not be exactly true. There may be places where they work the water harder than that. But at the time that it was given this name, it was the hardest working water in the world. So now I want to talk a little bit about what I've done with dams at Southern California Edison while I was in dam safety. To continue, our dams on the average are about 80 years old. Now, you know what happens when humans get older? Things start to wear out, right? Well, it's the same with things that we build. They're not built to last forever. And as they age, they start to deteriorate. And we have to constantly maintain them so that they're safe, because we have a requirement to provide safe, reliable, and clean energy for the future. And so we need to do rehabilitation on our aging dams. And this is just one of them that I worked on. And it has some unique features in it that you're going to see in some pictures that I'm going to show. This dam is called Meadows Dam. And some of you may have been up in this area before, if you've ever been up to Mammoth Mountain. This is just about 30 miles north of Mammoth Mountain, next to a community called June Lake. That's about 300 miles north of Los Angeles. This dam is also in what we call the wilderness area. Now that's an area that the federal government has set aside as wilderness, where no construction can be done. Nobody can go in there and develop. People can use it for hiking, fishing, camping, hunting, but they can't build in it. They can't own it. And it's intended to be preserved for future generations to be able to enjoy the wilderness as it was and as it remains for hundreds of years. Now, we had dams built back there long ago. So when the government established these as wilderness areas, our dams were already there. So they were willing to let us continue to operate those dams because they provided a benefit to the community in electricity generation and allowed us to continue to maintain them. But they put some very strict rules on us about what we could do and how we could work back in these areas. Now, this just shows you a picture of what it's like back at this location in the wintertime. And actually the snow would get much deeper than this. But you can imagine if it goes through, like I said, this dam is over 100 years old. So it goes through 100 years of this type of weather in the wintertime. And then in the summertime, it gets filled up with water. And then in the wintertime, all the snow back and forth, back and forth. It really wears on the dam. And what was happening with this dam is there was a lot of leakage, water that was coming through the concrete. It was still safe to operate, but there was a lot of water flowing out of the concrete. And also there were some issues with its design that at the time it was built were fine, but as we learned more and more about earthquakes and how dams operate, how they respond to floods and earthquakes, we found that there were some things that we had to do in order to upgrade this dam to be able to still operate safely. So this shows the dam with the reservoir completely drained. Now you can see in the bottom, there's a little bit of water coming in, and that's actually the creek that would flow normally. If this dam wasn't there, the water would flow through there. There wouldn't actually be a reservoir back here. There would just be a creek that runs through, or a small river that runs through and continues to go down to actually eventually ends up in Los Angeles, because we drink this water. So what we were doing here is because the dam was leaking, we were putting a plastic cover over the dam so that we could seal off the voids and prevent the water from seeping through the dam to the other side. But in order to do that, we had to drain all the water out of here and then come back and do our work. Now, we also found that one of the problems with this dam was that with the reservoir at high level, the load forces on the dam were such that in the event of an earthquake, it could potentially topple the dam because it wouldn't be able to resist the forces on it. So what we had to do is we had to come in and put in large bolts to try to tie the dam down to the ground. So what we did is we drilled holes through the top of the dam, all the way down to the bottom and into the rock that this dam is sitting on. Because you can see the mountains. If you look in the background of this picture, you can see that these mountains are just basically all rock. There's some trees, but it's lots of rock. So this dam's sitting on rock. So we can drill down through the dam and into the rock, and then we can put these large bolts that would go all the way down. We'd anchor them or cement them into the rock, and then we would tighten down on the bolt at the top to compress the dam into the ground, to hold it firmly against the ground so it can't slide or tip over. And we put in 10 of these across the dam when we were doing this project. Now, I told you that there's some unique parts about this project because it's in the wilderness. We were not allowed to use any transportation other than foot, mule, or horses. The helicopter could not land back here, and the only thing the helicopter could bring back was equipment that we could not transport either by person or by mule. So in this case, these bolts were probably on the order of 40 to 50 feet long and 3-inch diameter. So they were very heavy steel. So you couldn't bring those in a mule, or a person couldn't carry it. So we were able to use a helicopter. You can see down on the bottom, there's a little like a blue or green box there. That's a generator. That was too big to carry back, so a helicopter could take that back. But much of the things that we took back had to be done on horse or mule because it's the wilderness, and the wilderness did not allow us to operate transportation other than primitive transportation. So this is a picture of a pack train of mules and horses, and they're bringing supplies and the people who are going to do the work on the dam up to the dam. So we have horses and mules. I actually got to ride on a mule and on a horse several times on this project, just going back and forth. You can see the mules in the front. They have these what look like white bags on them. Those have equipment. They might have food or other supplies that we have, or supplies for the work that we're doing, tools. They could be carrying many different things up there. Then the other ones are carrying people, and we hire actually a company that does this. They have a pack station, and they load everything up and they take us up there. It takes about 5 hours to get from their pack station back to the dam, and it's about 5 or 6 miles. Or you can walk it as an individual if you don't do it this way. And I've walked it many times as well. Now we can't just go in and out this way because it takes so long that you wouldn't be able to get any work done. So what do? You set up a camp. You set up a camp back in the wilderness. And that's what this is. We have tents. We have a cook that cooks the food for us and keeps care of the camp. Get up in the morning, eat breakfast, go to the dam, do the work, come back at the end of the day, eat dinner, go to bed, get up and do it the next day. That lasts for 2 to 3 months. So they're back there in the wilderness. You can't get, there's no TV, there's no internet, there's no YouTube, no electricity. There's a fire, as you see here. You don't get any news of what's going on in the world. So you're isolated back here. You'll see people coming through here as they're hiking and camping, and you can say hello to them, but you're pretty much shielded from the rest of the world, so you don't know what's going on down here in the city when you're back here doing this work. This is a typical tent. You got a cot with a sleeping bag on it, and that's where you sleep at night and get up the next morning and go to work, come back, eat dinner, go back in here, sleep. If you like camping, it's fun, but it goes on for a long time. And you're at about 10,000 foot elevation. So it does get cold at night. And it gets colder as we progress through the summer, because we would work, as you're going to see, I think in the next slide, we'd work all the way up until the middle of November, toward the end of November. And you'll get situations like this. We're trying to finish up the project and everything's covered in snow. And so we have to come up every day and we got to clear out the snow so we can get our work done, and then go back and come back the next day, clear out the snow to get our work done. So it was an effort, a real effort. And these are the kinds of things that you might get to do as an engineer. You don't think about this, and they're not going to teach you this in school, but I, being an engineer, was back here doing this work, riding on a horse, flying in a helicopter, working in a dam in the middle of November, in a snowstorm. So it's a little bit different than what you might think of as the life of an engineer. But maybe that's one of the fascinations with the engineering career, is how diverse, how different it can be, from sitting at a desk doing designs or analysis, to out in the field actually implementing designs and analysis that you worked at your desk. So that's the end of my presentation. So I'd like to just ask, if anybody has any questions. And if you do, at this point, just come off a mute and ask your questions. I'm going to stop sharing.
I like to let the kids ask first, because I always write a bunch of stuff down. And it was so funny because you covered half the questions I was going to ask you already. And I was like crossing them out. I'm all like, well, that one's gone. But it was weird because I was going to ask you how you got to most of those locations, because I know your field is almost similar to mine, except for I work for AT&T in the field like that.
Okay.
And
Okay.
you do the same thing for SCE. And I was like, wow, I can identify with that, because I had an office that was in the high desert on the way to Vegas. And we couldn't get there with vehicles. We got to a certain point, and then we have to helicopter equipment in, or hike it up there. It's having an engineer title is great, but sometimes you got to get in the trenches.
Yeah.
I worked in manholes and stuff like that. So it's not a pretty picture all the time. But as far as your projects, from when they start to when they finish, how long is that process about?
Well, that's interesting, because with these dams, and most of them are going to be at the higher elevations where they get the really severe weather conditions that lead to this. Plus, the methods of construction 100 years ago, left much to be desired. The knowledge of reinforced concrete or just plain concrete was limited, and you find out the drawbacks to that 50, 75 years later when things start to deteriorate. But we have a very limited window of opportunity to work in these areas because we have to wait for the snow to melt so we can get in there and work. And that's usually happens in most years around June to July. And then we have, most of the time we have up through October to work in where the weather is going to be relatively stable. The temperatures will reduce, but you're not going to get snow. Or heavy rain, because that's going to make it impossible to work. This particular project, we worked up till the day before Thanksgiving because we had to get it done and we had to get our stuff out of there, most of our equipment. Now, we actually had to leave stuff behind, but it was equipment that would be stable and wouldn't present an environmental risk, that we could come back the next year when the snow melted and retrieve it. But we had 55-gallon drums of gasoline and diesel fuel to run the tools and generators with that we're using for construction. And we had to get those out of there because those could end up in the water and potentially breach and pollute the water. We had a generator, we had a drilling rig that we had to get out. So it got to the point where we couldn't stay in the camp any longer because the camp was completely covered in snow. I was up there for 2 days trying to shovel out the tents. And believe me, shoveling snow is hard enough. Shoveling snow at 10,000 feet is really, really hard. It's a workout.
Yeah.
So they had to fly us in and out on a helicopter every day. And we almost got stuck back there because we got flown in one day and then the snowstorm came in during the day. And we weren't sure that the helicopter was actually going to be able to fly us out. And we were starting to try to hike our way out because we couldn't maintain communication with the pilot because of our location versus where the pilot was in line of sight with our radios. And it wasn't until we started into the hike that we heard his helicopter coming back over. And of course, he was trying to get everybody out of there as fast as he could because there were high winds and the snow was getting heavier and heavier. And he wasn't sure each time whether he'd be able to come back, and he couldn't take everybody at one time because of the altitude and the limited capacity of the helicopter. So you could take 2 people at a time. And so we were like hoping that we could get everybody out of there because it wouldn't have been good if somebody had gotten stuck back there and had to survive for, even overnight in that kind of environment. Just very, very hard. So yeah, that's what we'd have to do. But for the normal transportation, we could walk it or a horseback or mule. That's the law. That's the law in the wilderness, is that you have to use primitive methods.
Right.
So that's what we'd be stuck with. And I've done it all. I've hiked it. I've rode on a mule. I've rode on a horse. I can tell you this: if you ever get a choice between a mule and a horse, especially if it's in those kinds of conditions, like up in the mountains on trails, pick a mule. Don't take a horse.
I was going to say the mule probably works better.
much better, much smoother, much more sure-footed. The horses were just, I was scared because at times we'd be on the edge of a cliff, like where it's just a sheer drop off of like 100 feet on one side, and then they're just climbing up this trail. And those horses, you just never knew, because they would stumble every once in a while, and you just like, please get through this one section. Because there was one time that the packer lost a horse. Fortunately, nobody was on it, and it fell down into this about 100 feet down, and they had to leave it there because there's no way to get it out. I mean, it was dead when it hit the ground, but they couldn't get it out of there, so they had to leave it there. I think they said they actually went in with some explosives to try to, I guess, blow it up so that, because it was creating a lot of, that's a very heavily hiked area, and it was creating a lot of odor and flies and stuff from the decaying body. So these are the things you get involved with when you're
Yeah.
that don't have anything to do with engineering.
Not at all.
But it keeps things exciting. I mean,
Newfound respect for electricity.
yeah, these
Oh my goodness.
yeah, these facilities were quite something. I mean, these were record setters back when they were built, as far as the amount, the length. This originally was built to provide electricity to the mines in Tonopah, Nevada.
Wow.
They built this system to provide the power to another state. And when they ran those power lines, those power lines held the record for the longest transmission of electricity in the world at that time. You know, it's nothing today, but back then this was a big deal.
I know where Tonopah is.
Yeah.
It's in the middle of nowhere.
Yep. I guess it is.
And believe me, doing the work I do, I know where the middle of nowhere is too.
Yeah.
I've been there several times, but
Yep.
the one in near Fresno, the dam you talked about earlier.
Yes.
That
Yes.
one's still operating?
Yes. That whole system up there in Big Creek is still operating. The multi-arch dam, is that the one you're talking about?
Yeah.
Yeah, that's still back there. It's called Florence Lake Dam. It's actually located at the end of I forget the highway number now. But if you went straight over the mountains from that dam, if you went straight over the mountains east, you drop down into Bishop, California.
Oh, okay.
So it's interesting because we have dams on the Bishop side, and we have dams on the Fresno side, but they operate in distinctly different ways. On the Fresno side, we have lower elevation dams, but we have much more water. The volume of water that comes out of that area is much larger. So we can generate much more electricity, even though we don't have as much what we call head or height of water. Our highest dam is at about 7,500 feet. We go over to the Bishop side, and we have dams at 10,000 feet or higher.
Oh, wow.
But the water, the amount of water that we have is much less. So when you look at the two sides, on the Fresno side, the Sierra Nevadas are sort of gradually increasing in altitude.
Mm-hmm.
When you're over on the Bishop side, it's very steep. You think Mount Whitney over there.
Yeah,
You know, when you look at those mountains, you can see that they're very steep. There's no gradualness to it. It just goes straight up. And that's why you can get these high elevations. But over on the other side, it's very gradual as it comes down to Fresno. And so you don't generate as much power, but you can generate off the same river multiple times because you start out at such a high elevation. So we have Bishop Creek. There are 5 power plants on Bishop Creek producing power as they go from the high Sierras down to Bishop, California. The same river, same water generating power.
I think the highway, is it 168?
Yes.
Okay, that's what I thought.
Yeah. It goes up through Bishop. When you come into Bishop, it heads up west, and it goes up to Lake Sabrina.
Oh.
And that's the end of that highway. And then if you could go over those mountains, you could eventually drop down into Florence Lake Dam and pick up the highway and take it all the way down to Fresno. And actually, I had people, I would be at Florence Lake, and I've had people actually come up to me that said, how do I get to Bishop? Because when they look at a map, they see Highway 168 and they think it goes all the way over the mountains to Bishop. And I'm like, you go back the way you came and go all the way around down to Bakersfield and then come back up the other way. It's about 8 hours.
Another 3 hours.
Yeah, or you can go through Yosemite, but either way is going to take you about 8 hours to get to Bishop because you can't get through this way except on foot.
And I wish you could, because my parents live right on the other side of like the Visalia area in Pahrump, Nevada, and it'd be just a straight shot, right? But
yeah,
you got to go all the way down 3 hours and then across and then go all the way back up another 3 hours. It's just,
I've had to do that. I've had to go from Bishop to Big Creek, and I've had to decide, do I go through Yosemite or do I go down through Bakersfield and up the 99?
Yes.
And it's about the same amount of time. It's a lot shorter going through Yosemite, but if you've ever been through Yosemite in the summertime, you know, that can take you hours just to get through the park because of
Yeah,
all the traffic.
all the people. And then in the
Yeah.
winter time, you don't even want to try it because the conditions.
Oh, yeah, but yeah,
Are
yeah, yeah, exactly. If the road's even open, you
yes.
know, to go up through there. But yeah, it's some interesting things that I learned being in dam safety. You know, when I came to work for Edison for my first 3 years, I didn't even know Edison had hydroelectric power
Wow.
until I was looking to change jobs at the company, and I saw this dam safety, and I'm like, we have dams? And somebody said, oh yeah, we got a whole series of them. You know, we generate a lot of electricity from them. And I'm like, I've never heard of them. I got an introduction to all of this stuff, and it's pretty amazing. It's a lot of history with, especially with the Big Creek system over there. That's really something. If you're ever able to go up in that area, you can go to Big Creek. It's a little town. It's, you know, it was the town that was built when we were building all of this, when it was all being built. But they have a museum there that you can go through, and you can actually see pictures and relics from when they were building this. They built a railroad that went from Fresno to Big Creek to move workers back and forth during they'd move them up there during the week, and then they'd bring them back down on the weekend. And there was a saying that, you know, they get paid on Friday and they come back broke on Sunday.
That's usually how it is too.
Yep. And, you know, there was a lot of activity going on down in Fresno that was set up just for these people, because they had well-paying jobs for that time of the year, or that time of life in America. And they called this railroad that was a San Jacinto something or other, but they slow and jerky. It was SJCO, and it was slow and jerky something or something. But because the train was very slow and it was very rough riding on
Trying
it.
to get up and down.
But it's amazing when you see what they built back there. It's like, when you think about how they did it with just brute manpower and blasting and drilling, and they built this stuff so fast. They started in 1914 and they were generating power from the first plant in 1917.
Wow, that's great. We can't even do that now.
No, we couldn't even get something like that permitted in that
No
time,
way.
much less build it.
No way. All right, guys, it's 5:37. Anybody got any more questions before I let John go? And John, by the way, this was very interesting. I really enjoyed hearing about it. And we usually rotate our presenters from time to time. So we hope you don't mind coming back to talk to the class later on in the year. Usually is about 7 months down the road, but it's well worth the time, the time frame that when we get back to you again, because then it's more like a refresher course at that point.
Absolutely. I really enjoy doing these things. And so, you know, I'll jump at the opportunity. I would say, you know, if you do reach out to Speakers Bureau like you did this time.
Yes.
But when you reach out to them, if you want me to come and speak, then be sure in your request that you specifically state, you know, we want John Stoessel to come, because if you don't, it just goes out on a board to all the Speakers Bureau people, and then the first person to respond to it is the one that grabs it.
Yes.
And you know, there's a lot of different topics that we have people capable of speaking on. It's